Okay, we're looking at problem 89, and to take away from this problem, be sure you remember that what you need the skills you need to be able to demonstrate here is that you know what the trend is in atomic radius, and that you also know what is going to happen to the radius of an ion when it either gains or loses electrons. And so in this first one, we see hydrogen and helium, and you are supposed to identify which one has the smallest radius. Now I'm looking at this table I was showing you in a previous program, and I'm looking here at hydrogen and helium, and I'm looking here and saying this is a problem because this does not show the trend real accurately. And if you want to see this in a different form, finding the page number in your book, it's kind of at the end of chapter 7, and I'm looking in a table, page 314, that I think is a more trustworthy table as far as what happens with the atomic radii of the noble gases. And so what we'll see there is that as you go across, you get smaller and smaller diameters, and that's the trend. And so helium is actually smaller. And now looking at part B, we're looking here at chlorine, indium, and selenium. Now chlorine, indium is atomic number 49, and selenium kind of halfway in between. I think it's very clear there that chlorine is the smallest of those three elements. And the trend is, as you go down a group, as you go down any period, you're going to be looking at larger and larger elements. Elements 120, 119, and 118 at the time of the publication of this textbook were not had not been manufactured yet. So these are definitely predictions that you're making in this particular case. And element 118, and I'm disagreeing here also with at least the answer in my textbook key. Element number 118 would end up being a new noble gas. 119 and 120 would come down here on the next line. And of course, I'm still not quite drawing this right because it would be actually the next line down. So 119 would be the smallest of these. And now I'm looking at the problem and saying, is that actually what I was looking for? Because I'm seeing a different answer when I glance in the book. At any rate, the answer there appears to me to be 118. Excuse me. And so you should be able to finish out D. I'm going to skip to E for just a moment and have you consider the trend in size of ions compared to atoms. And basically, for any atom, if this was the sodium atom, whatever its atomic radius is, if you gain an electron, if you go to Na minus, it's going to have more negative charges than there are positive charges in the nucleus. So that electron is really going to make the atom increase in size because it won't be held as tightly to the nucleus. Of course, if you lose an electron, anything that loses electrons, especially metals, become much smaller because they're losing their valence shell. So when sodium loses one electron, it loses its valence shell. Also, there's a greater charge attraction for the nucleus because now the nucleus is attracting fewer electrons, and so that tends to pull the electrons in more tightly. So the smallest one here would definitely be the sodium ion. Let's see, moving on to 90, you're going to be looking at the same kind of trends, so see if you can finish that up. Now, moving on to number 111, oops, let's see, I think we're going to just skip through these in number 90 and move to problem 111. which is, to me, it's just one of my favorite problems in the textbook, because it's a fascinating application. A lot of you have seen photogray lenses. They're the lenses that when you take glasses out in the sun, they get dark automatically. And I don't know if you've ever given any consideration to the chemistry behind that. Well, the chemistry is that this compound is incorporated into the lens, silver chloride, and silver chloride is sensitive to light. And it turns the silver chloride, or basically the silver +1 ion, into a silver atom. And that takes an input of energy to do that. So the silver metal is formed, and it causes the lens to darken. Now, it says here, oh, I didn't get this, this is a 3.10 times 10 to the 2 kilojoules per mole is how much energy it takes to do that. Now, assuming all of that energy is supplied by light, what's the maximum wavelength of light that can cause this reaction? Well, this is the amount of energy for a mole of the silver to be reacted. And what this question is how much light does it take to change one atom? So we're going to take this 3.10 times 10 to the 2, that's the kilojoules per mole, and we want to just change this moles to atoms. How much does it take to change one atom to one atom of silver? So you remember that 1 mole is 6.02 times 10 to the 23rd, and so we would now be in kilojoules per atom. I'm also going to just change that to joules instead of kilojoules. So that's, we're going to multiply by 1,000 to do that. And so putting that all into my calculator, I'm going to get 5.15 times 10 to the negative 19 joules. Now that's the energy required to convert 1 silver ion to 1 silver atom in this particular reaction. So the question is, what wavelength of light does it take to do this? So we have an energy here, and we know we have several equations that, one that says energy is Planck's constant times the frequency, and another that says frequency can be calculated by the speed of light divided by the wavelength. And we have these relationships. Here we have energy. The energy is, and I'm just going to put these two equations together, I think, first of all. Energy equals H, and frequency is C divided by wavelength. So I'm going to substitute in the numbers that I know here. Well, let me rearrange and rearrange this equation to solve for wavelength first of all. Let's see, wavelength is going to get wavelength by itself. I'm going to have Planck's constant times C divided by the energy. That's how it would rearrange. And so check out the algebra on that if you want to. Make sure I've got that right. Planck's constant is 6.626 times 10 to the negative 34. That is joules times seconds, or the units. C, we've been just using 3 times 10 to the 8 meters per second. And energy is 5.15, we just calculated that up above, 5.15 times 10 to the negative 19 joules. So my joules are going to cancel, my seconds are going to cancel, and I'm going to be left with my wavelength in meters. And what wavelength did you get? Something on the order of 386 nanometers. Actually, what you calculated was 3.86 times 10 to the negative 7 meters, and that's 386 nanometers. And so it takes at least a wavelength of light that short. Anything longer more into the violet spectrum will not have enough energy to cause that change. And so we're kind of down here in the ultraviolet range that makes that change. And that's why it knows when you go outside, is because you're seeing sunlight and lots of UV light and things like that. So that's how photogray glasses work. Thanks. Come again next time.